In this video, I want to introduce the logarithm function. All right. The logarithm function is written this way. Log, you'll see a number like such as maybe 4. Okay. You can have different numbers and they refer to different versions, different functions, different logarithmic functions. Okay. You can have like the log of 2. You can have the log of 10. Okay. And the way that we refer to these logarithm functions is the following. So the first one, we would say, to use the jargon, this is the log or logarithm. The logarithm of x to the base of 4. Okay, the second one is the log of, I'll use the log, this abbreviation this time. The log of x to the base of 2, and then people can really shorten it. On the last one, you can say the log of x base 10. All right, so all of those are ways people refer to various logarithms. Okay, let me now give you the definition for the following, a general log. Suppose you wanted to know what the log to the base a of b is. So you're plugging in the number b into the log to the base a. The way you would say this is the log of b base a, perhaps. Okay? What I'm going to do now is I'm going to give you a sentence that defines what this means, and I want you to memorize it. Okay? In a couple days, weeks, months, years, you may at some point blank out and say, now what in the world is that weird log function again? Okay, if you can burn this sentence into your brain, then when you blank out in the future, if you can recite it, that'll help it to come back to you. All right, so this is the exponent a needs to equal b. Okay, short little sweet sentence. Okay, the log of b base a is the exponent a needs to equal b. All right, several examples will make that clear what that means. Okay, maybe I'll put a box around it. So let's replace a and b with some numbers to make it more concrete. Suppose I asked you for the log of 8 to the base 2. Okay? So what you need to do is think about this question. 2 raised to the mystery exponent equals 8. Okay? Can you see that 2 cubed is 8? So we would say that 3 is the exponent 2 needs to equal 8, or for the power to equal 8. So therefore the log of 8 base 2 is 3. Okay? Let's do another example. What about the log of 81 to the base 9? Okay, well, 9 to the mystery exponent is equal to 81. What power of 9 gives 81? Isn't it 9 squared? 9 squared is equal to 81, so this is equal to 2. Okay, if that made sense to you, and go ahead and write down the definition of the log on your notes somewhere in the box, then try to do the following examples, please. So the log of 16 to the base 4, the log of 2 to the base 4, the log of 1/4 to the base 4, the log of the, let's see, how about the log of over 16 to the base 4. Try to do all of these, please. Okay, so the definition of log, well, in this, for the first case, it's the exponent 4 needs to equal 16. So 4 squared is equal to 16. For the second example, 4 to the 1/2, or the square root of 4, is equal to 2. For the third example, 4 to the minus 1 is equal to a fourth. For the last example, 4 to the minus 2 is equal to 1 over 16. So therefore, we just peel off all those exponents. So the first one, 2, and then 1/2. For the next one, then minus 1 and minus 2. Okay? There are a couple of bases that show up more often than any other bases. Okay? They are the following. The log of to the base 10 and the log to the base e, where remember e was that irrational, never repeating, never terminating decimal. E equals 2.71828 ... Okay? These come up so much that we actually have abbreviations for these. Okay? The log to the base 10, because that gets used so often, people just omit writing the base. So when you see people write this black version, if they don't write explicitly what the base is, you can assume it's 10. Okay? For the base e, that the abbreviation for a log to the base e is ln. Okay? Now, 10 is called the common base because it's so common, and e is called the natural base. It's in various applications, it's the natural choice to use. Okay, that's why the abbreviation is ln. The n refers to natural, as in natural log. Okay, so let's finish by talking about the inverses and talking about graphing. So the exponential functions and the logarithmic functions are inverses of each other. Okay, the inverse of the function 2 to the x, f of x equals 2 to the x. Let's call the inverse function g of x. That is the logarithm to the base 2 of x, or log x to the base 2. Okay, you can convince yourself of that by plugging in a couple numbers. F of 1 equals 2. F of 2 equals 4. And let's see, g of 2 is the log of 2 to the base 2. But to make 2 equal 2, we need an exponent of 1. All right, that makes sense. If we plugged in 4, to turn 2 into a 4, we could raise it to the second power, so that would give 2. So indeed, you can see for those two examples at least, it's the log is behaving like the inverse. Okay, now let's talk about the graphs of logarithmic functions and compare them to the graphs of exponential functions. So let me remind you that exponential function graphs, like 2 to the x, 3 to the x, they have a horizontal asymptote, a y-intercept of 1, and they take off like a rocket for increasing x. Okay, as you move to the left, again, you have a horizontal asymptote. The logarithmic function has an x-intercept of 1, an x-intercept of 1. It also grows, but very slowly. Okay, the logarithm function has a vertical intercept, an x-intercept of 1, and grows unbelievably slowly. Okay, to give you an idea of something that grows as slow as the logarithm, think about how big you have to make a number, how much a number has to grow in order to add more digits to the expression. Let me show you what I mean by that. So if I wanted to turn, let's start with the number 1. If I wanted to turn that into a 2-digit number, I could add 9. If I wanted to turn it into a 3-digit number, I have to add 90. If I want to turn it into a 4-digit number, now I have to add another 900. If I want to turn it into a 5-digit number, I have to add 9,000. Okay, I've already added 9,000. Actually, I've added 9,999 from the original number just to get to 5, for crying out loud. The y, if let's say if this was the y value, okay, so y equals 1, y equals 10, y equals, or excuse me, no, these are the x values. And I'm making up a function here. I'm making up a function where the y value is going to equal to the number of digits in x. Okay, so the y value for 1 is 1, the y value for 10 is 2, the y value for 100 is 3, the y value for 1,000 is 4, the y value for 10,000. The point I want to make is just to get to y equals 5, we already needed to go up to 10,000. Okay, and we're going to keep adding these more and more, these ridiculously huge numbers, just to make y keep creeping up by 1. Okay, so that just gives you a sense of how painfully slow the logarithm grows. Okay.